correctly? Yeah, there's no calculus on the entire problem set. Calculus. We're going to be we're not going to be, as you're going to see, we're not going to focus too much on the wave functions and kind of that stuff for harmonic oscillators, because this is a problem that we're going to see this starting today that we can just directly apply to chemistry, the chemical kinds of things, and we'll kind of focus in the context of chemistry instead. In particular, molecular vibrations. So we'll do a little bit of work with this stuff today. I've got some pictures to show you. And then what we're going to do is move on to kind of chemical applications. And then we'll spend a good amount of time on that. So let's recap where we were. We've got we're treating we're working with kind of diatomic molecules here, like Cl2, HCl, H2, N2. Just two balls attached with a spring. And we've got a spring that has a fixed force constant and a fixed stiffness. With two masses attached to it. And we solved that problem quantum mechanically. And we got these kind of somewhat complicated wave functions, but we'll look at them very carefully today and get a sense of how they look. And the important thing about these wave functions, again, because this is the first system we've seen that has a non-zero potential energy. Right? Potential energy is harmonic. It's x squared. Right? So there's a value of the potential at every point for the spring as a function of its displacement. And that gives us different wave functions than we solve for the particle in the box. And these are functions that look like Gaussians, right? Bell curves. And in order to make them orthogonal, right, we need to remember we saw that Gaussians, a product of two Gaussians gives you another Gaussian. Take two of these and get one back. So they're never orthogonal to each other. The integral of one Gaussian is non-zero. The integral of product of two Gaussians is non-zero. So it can't be orthogonal. So we add these orthogonalizing functions, these Hermite polynomials, which I kind of introduced, which are just functions of x. And there's a bunch of constants that we can look at later. Right, we'll kind of analyze this problem carefully as we go through, and we'll pick out the more important aspects that we should pull out from this system. But in general, we have a set of wave functions here. I've written a series of them right here. There's more in my notes, and if you have the textbook, there's like the first 10 are tabulated. But the idea is that we have some wave function that's actually distributed over infinity. All right, that basically the bond can be any length. And so that's because we have these Gaussian wave functions. Gaussians are defined from negative infinity to positive infinity. And what we actually see is that, so for the ground state, the Hermite polynomial is just a number one. It's not a polynomial at all, it's just number one. Our wave function is just a Gaussian. Right? So it just looks like a bell curve centered at the middle of the potential. I'll have some pictures of these in just a minute. And then as we go up a quantum number to the first excited state to the second excited state, that Hermite polynomial, this thing right here, gets an extra order of x for each level. So the psi1 is x to the 1, psi2 is a quadratic, x to the 2, psi3 has an x cubed function, and so on and so forth. And what that actually generates is a little bit of oscillatory behavior inside of the potential. So outside of the potential, it just looks like an exponential function. It just decays out to 0 on the edges, but inside it oscillates. Right? And it oscillates in an orthogonal way, just like sine functions, right? So it's almost as if this polynomial right here embeds a little sine or cosine wave inside of our wave function that inside the potential. So inside the potential, it has wave-like behavior. When the spring is bouncing back and forth between its turning points, it has an oscillatory behavior, and then on the outside, it decays as an exponential, e to the minus x squared. On the outside, like a free particle. Okay, so even though this looks funky, and that's a polynomial times a Gaussian, it's not a sine wave. It has this sinusoidal behavior in it, this oscillatory behavior in it, right? Just like our particle in the box. All right, so I'll look at these more generally in just a second. All right, so the most important number. Think about what our wave function is defined by. We've got a bunch of numbers here. But the two most important numbers is this number V, which can be any integer 0 or greater. That's our quantum number. That specifies which state we're in. And this system in particular is unique. System in particular is unique because 0 is allowed here. Remember, it wasn't allowed for the particle in the box, but you can have a spring with 0 excitation in this system. Size 0 exists. All right, and the most important things that are determined again is this number V. It's just a number, not a big deal. Just a number, and then we have this alpha, which kind of shows up everywhere in all three terms. Normalization constant is a function, part of the orthogonalizing function. It's a part of the exponential alpha, and alpha is just a number that depends on the Horst constant and the mass of the system, and it has units inverse meters squared. So let me get my pen. I'll just make a note there. Find my pen. There it is. So the units of this are inverse meters or inverse length. And the reason why it's inverse length is because in exponential, everything inside of an exponent needs to be unitless. You can't take an exponential of a united value. It's undefined. That would be e to the unit, which doesn't make any sense. So this whole thing needs to be unitless. We have an x squared that has units length squared. So alpha needs to be length to the minus squared power, L to the minus 2. So this is units of meters squared. And what M does, we'll look at this a little more carefully. I have a nice some code that'll plot these for us. Alpha is just a function. If you keep mu constant, for instance, it's just a function of square root of the stiffness. And as we'll see, what that determines kind of is the sharpness of this potential. All right, as alpha gets bigger, I'm going to double check. As alpha gets bigger, this potential gets sharper, which means that the spring is stiffer. You have to apply more energy to stretch it. And then as alpha gets smaller, this potential gets wider, okay? Which means we kind of think of it as a floppy bond. Right? You can move it a lot without changing the energy. Right? So alpha kind of tells you something about the shape of the potential, and that's just a function of the bond parameters itself, the mass and the stiffness. So all of the relevant information about the bond is encoded in here. Alpha, all built into alpha. Okay, so let's look at some pictures of these. Well, actually, let's do one more thing. I forgot we should talk about the energies of these wave functions. That's important. We're going to want to do spectroscopy on this after a while. And so the question is, what are the energies of this system? And I won't go through the derivation of this. It's not too hard to do. But what you find is that if psi v of x is a harmonic oscillator wave function, then the energy of that state, E sub v, is h bar omega v plus 1/2. An amazingly simple formula. Remember that v is just a number between 0 and infinity, just a positive or a 0 number. And omega here, we've already defined, it's the same omega as our frequency of our wave. For oscillation, it's the square root of k over mu. Right, so we have this amazingly simple formula. Just says that we have, in some sense, a harmonic frequency. We'll have to double check the units of h bar omega in a second. Let's see what the units of that are. But it's just some number. H bar omega is a number dependent on the type of bond we have times v plus 1/2. It's super, super easy calculation thing to remember. And let's think about the consequences of this function, energy function. We can draw some energy levels, right? And so let's look at, for instance, 0, 1, 2, and so on. All right, what are the energies of them? Well, V equals 0, we get 1/2 h bar omega. So the energy of this state is 1/2 h bar omega. V equals 1. Now we have a 3/2 h bar omega. And then the next one is 5/2 h bar omega, right? You can probably see the trend now, right? If we think about what are the energy differences between these, well, the energy difference is just h bar omega. All right, so this is why we call it a harmonic oscillator. The harmonics are the fact that the allowed frequencies or energies of our spring. Well, again, we'll check the units really quickly, but the allowed energies or frequencies of our spring are separated by units of a fixed frequency, right? They're fixed length, fixed distance apart, equally spaced. Right, so you can kind of think of this in some sense as h bar omega is your fundamental note on the piano. You know, some piano string that has this frequency h bar omega. You have a 0 oscillation of the spring, which is you don't press it at all. You don't hit the key to excite it. And so this spring actually always has some net energy, 1/2 h bar omega. It's not energy equals 0. We'll have to think about the consequences of that the energy is not 0 for E equals 0. So that's one, you can think of that as your fundamental key, and then your frequency of a spring, and then you have your A note. Let's call this the A note. This is your A note, and then you go up an octave, which is the whole frequency, h bar omega. You're at the next octave of that note, which is that energy 3/2 h bar omega. You go to the next octave, which is another step of the fundamental frequency. You're at H2. Right? Each one, if you some sense, each one of these levels is a different octave of the same pluck, h bar omega. Right? That's what we mean by harmonic, because it again follows a harmonic tuning. That we have some fundamental tuning h bar omega, 1/2 h bar omega, and all of our notes are octaves of that fundamental note. Right, so that's what we mean by harmonic in the same sense that it's like audio or acoustics. They're all equally spaced. All right, let's double check our units. Well, again, I've just said that the energies are equal to h bar omega. Right, just by definition. So we know that the units of h bar omega are energy. If this unit has, say, for instance, units joules, and therefore we know h bar has units joules seconds, and therefore omega has inverse units of seconds, right? It's a frequency, just like we expect. It's per second. All right, so again, if you have the idea that, again, every bond, every molecule has a fundamental tuning to it, h bar omega, and every allowed frequency of that bond is an octave of that fundamental. All right, well, let me just show you some pretty pictures. So let's just look at these wave functions a little bit. So what I've put in here, just a little script I wrote during office hours today in Python. Let me see if I can make this full screen for you guys. Single document. That's good enough, probably. So what I've put in here are the kappa and the mu for HCl. Okay, there's some other terms in here that we can talk about later, but I basically set this. I'm going to set this problem up so that we reproduce the values for the HCl bond. Okay. These values you actually calculate on the homework, so we won't go through them. But they're just values that tell you calculate the stiffness of the bond And of course, the reduced mass of the bond is very easy to do. You know, the masses of hydrogen. So I set up some calculations. And then what I have here is a couple functions that calculate the energy of a given state V, and also the harmonic oscillator wave function for that state. And what I've built is just a little script that takes, in this case, the first 5 wave functions of the harmonic oscillator and plots them at their energies inside of the potential. Let me make this a little bigger for you guys. So this is what the harmonic oscillator looks like. Let me make it a little smaller so we can see it. That should be better. Right. So on the x-axis is bond length, in angstroms for HCl, and the y-axis is energy in a unit called wave numbers, which is the unit we use in infrared spectroscopy. It's a unit of energy. We'll talk about it today. And so each of these dash levels are the different energy levels. Right, so this is the V equals 0 down here, V equals 1, V equals 2, V equals 3, V equals 4. And these are the wave functions plotted on top of them. And you can see that within the potential, right, and within the quadratic potential, our wave functions look a lot like the sinusoidal wave functions we had in our box, our particle in the box, right? This kind of looks like our V equals 1, our N equals 1 wave function, just a half a period. This looks like a whole period. This is a period and a half, 2 periods, and so on and so forth. All right, just like before. All right. So the behavior, in some sense, of the harmonic oscillator is inside the potential is very much like a particle in a box. The only difference here is that, in some sense, at each energy level, the box is getting longer. And you can think of the box as being this point to this point, and as the energy goes up, the box gets a little longer. The system delocalizes. But in general, it still oscillates like a normal wave function. Okay? But the important thing is that because this potential is finite, right? It's not an infinite wall. As we saw, you can leak out the sides, right? And you can see that here. Let me actually plot psi squared here instead, right? So let's look at the square of this wave function. So we'll do this times 2. There we go. Right, again, it looks just like our particle in a box. The important thing is that at the edges, right, the wave function doesn't go to 0. It continues on. In fact, it doesn't go to 0 until x equals plus or minus infinity. So there's some part of this potential, this wave function, because the potential is finite, there's some probability that in fact the bond will be slightly longer than its turning points. Right? There's some probability it's outside the potential. And you can see that that's the case everywhere. They all have this slight extra probability on each side where they could be outside those turning points. Okay, so this is, again, it's sinusoidal inside the box, like the particle in the box, but a box that in some sense is varying in size as a function of energy. But the wave function is defined outside the box as well. Okay, it's leaky, naturally leaky. Right, this has deep consequences, of course, for chemistry. We'll have to think about this a little more carefully. But imagine that you have a bond that you want to pluck, right? You want to pluck an atom off a bond to react it, right? You want to take a hydrogen off and replace it with a chlorine or something like that. You know, just a substitution reaction. But in some sense, that reaction is going to be a function of that bond coordinate that you got to break, right? You got to stretch that let's say carbon hydrogen bond to break it, and then pluck and then bring in and then so the other atom can come in and replace that hydrogen. All right, so in order to break a bond, what do you have to do? Well, you got to take both of those atoms and pull them to infinity, right? You got to break them apart. That takes a lot of energy. Right? I mean, to make the bond go to say, right, this is so 1.3 angstroms here. 1.3 is the bond length of the system. If you want to go to 2.6 angstroms, right, how much energy do you need to put in the system? Well, you got to put in so much we can't even see what it is, right? So it's tens of thousands of wave numbers on this energy scale, right, to break the bond, right? So in order to break that bond, you really, really have to put a lot of energy into it. But the thing is that you don't always have to do that, because if you think about, let's imagine that in some sense, that if the bond is within these 2 points, it's covalent and connected, and if it's outside the potential, it's in some sense labile. It's able to be broken apart. Right? So think of this as like being an on-off switch for reactivity. If the bond's inside the potential, it can't react. If it's bonds outside the potential, it can react. Right? So even if we can't pump it full of energy to get it stretched and to get it weak, there's always some probability that we'll find the bond, that the reactive system will find the bond outside the inactive region, and it will react as if it were stretched. Some probability we'll find it stretched. And so sometimes you would think, okay, I gotta put in X amount of energy to break this bond and start the reaction, but the reaction just goes anyway, even though you didn't put enough energy into it. And this is largely the reason why that happens, is that whatever you prepare, state your reactive molecule, you prepare that bond in a certain temperature and position, and it's always got some probability that it'll be like break apart just spontaneously. And so you'll get some kinetics. The reaction will go forward even though you don't think you have enough energy for it. And so the bond will in some sense tunnel and break apart. All right, we call that pre-dissociation. And you'll get the reaction to go even if you don't have enough energy. All right, this happens all the time in chemistry. It happens especially in the atmosphere, places where you don't have a lot of collisions to stabilize reactions. These tunneling reactions where a bond is like somehow tunneled out of its potential and is now reactive, these happen all the time. Tons of molecules do this in the atmosphere. All right, so again, I can draw more and more and more. All right, we just for shits and giggles, let's just do it. Right, and in theory, this goes on forever and ever and ever. That's maybe a little too much. Right, I can just keep adding levels and levels and levels. All right, theoretically, this bond, right, the system will stay bound. Right, this potential in some sense never breaks apart. Right, there's infinite bound levels for your molecule. Right, so what that means is that no matter what I do from the point of view of the wave function, this wave function, no matter how much energy I put into the bond, it will always stay bound. It'll get stretched further and further and further, and will vibrate faster and faster and faster, but it won't break apart. Right? There's no dissociation. Right? So the harmonic oscillator, we've heard, in some sense, we've discovered a problem. Is that what this is telling me? Just like our infinite particle in a box, the only way to escape out the box, if you will, is to sneak through the wall, right? Through this tunneling process, right? This little probability out here. Otherwise, there's no escape from this potential. This potential goes up to infinity. It's 1/2 kx squared. It's fine for every point x. So the only way technically to escape out of the bond is through tunneling. But that doesn't make any sense, right? Because we know that if you put enough energy into a bond, it just falls apart. So you can put enough energy into a bond that it doesn't just tunnel, it just falls apart because you put enough energy to break it, right? There's some bond strength, right? So you can imagine that if I pump my energy all the way up to the bond strength of HCl, which on this scale is about 43,000 wave numbers. So at this point, right, the idea is at this point, we don't have a bond anymore. Bond has been broken. But what this potential tells me is that not only is it not broken, it's still a bound bond, it's still vibrating, it's still stretched really, really far on average. It's oscillating very, very rapidly, but it's still together. But you know, if you put in 43,000 wave numbers of energy, the HCl would fall apart. The bond is broken. So the problem with the harmonic oscillator approximation is that it doesn't work globally. It's a local approximation of how a bond moves near the bottom of the energy. So at low energy, the harmonic oscillator is a really good approximation, but it doesn't predict the most fundamental property of a bond, which is that it falls apart if you put enough energy. Right? It has to have a bond energy. Right? So we're going to have to figure out how to correct this so that we can have a model that looks harmonic near the bottom of the potential, but at high energy, it falls apart and breaks apart. Right? Something that predicts bond association, a bond energy. So we'll have to return to that. We've already gotten some sense of we'll eliminate this. Any questions? Okay. So we can go through integrals and averages and things like that. But again, if you think about it, not really that much is different here than it was for the particle in the box. If I ask you what the average position of the bond is, right? The average value, the expectation value of X, oh, you would say it's right in the middle, right? And it's easy to see that for any of these states, the average position is right in the middle. It's even about the middle of the potential. Right? So just like the particle in the box, the average value of X is 0, or whatever this point is, 1.3, the bond length. And then, the average value of the momentum is 0, because again, it could be moving left or right equally. Momentum squared is a non-zero value. It has some total momentum in all of the states because it has energy in all of the states. So in some sense, none of the properties of this system are really all that effectively different from the particle in the box, except for now that we have this behavior on the edges. And of course, the wave function looks a little different too. Okay, so I want to do some analysis of this problem. And I want to come up with a new model for the potential that now includes dissociation, bond dissociation. We want something that when you put enough energy into it, falls apart, it breaks apart. So let's do a little bit of math analysis here. And then what I'm going to do is suggest a new function for the potential that looks like the harmonic oscillator, but includes this bond dissociation. And we'll learn that there's some new features that we get from this. So the first thing I want to look at, right? So we've got this v of x 1/2 kx squared. Right, that's our potential. Just looks like a quadratic at x equals 0, centered at x equals 0. All right, I'm going to shift this bond. Right, so what I'm going to do is I'm going to go into experiment. And measure the average length of x. All right, we can take an integral of stuff. We have a box that measures the average position. And we define this position to be what's called R sub e. It's average position. This is what's called the equilibrium bond length. Right. And so I'm going to rewrite the potential as R minus R sub e, which is 1/2 k R minus R sub e squared. Right, and all that does is it just shifts the potential horizontally over to where it minimizes, where the minimum values at R sub e now. Right, so I've got a potential here, and at some positive value R sub e, my potential is 0. Right, just like that. Okay, so I've just shifted it over by R sub e. Right, this is kind of what the harmonic potential looks like for the bond. Bond has some equilibrium length, and the potential is 0 at that point. And we can measure that experimentally. And in fact, the homework talks a lot about how we measure this value experimentally. All right, what I want to think about is, I want to think about this function. Let's say, for instance, that this function, right, this is the harmonic approximation. All right, but what if the function isn't actually harmonic? Right? What if, for instance, the potential kind of deviates in some way? Right? Certainly the potential stiffness of my spring, that big slinky I had, deviates. K is not the same value everywhere. As I stretch it, the bond gets weaker. It gets floppier. It's not always as stable as it is smaller. So K actually depends on the distance. And when K varies on the displacement, the stiffness varies on the value. In some sense, K is a function of X. Like the force constant is dependent on the displacement of the spring. Then you're not going to have a potential anymore that's quadratic. You're going to have a potential that's more complicated. All right, so we can think generally about that. All right, so let's think, what if it's not a harmonic? What if it's an anharmonic bond? Right, and so what we can do is think about the potential as some sort of polynomial, right? So we've already used 1/2 kx squared. Right, so what if we start adding terms on top of that, an x cubed, x to the fourth? Right, so we can think about a little bit as think of v of x or r minus re. Right, it's some function, some smooth function. Right, and we can write it as as expansion in a polynomial. We can write it first with a constant term v of r sub e. Right, so this is our zeroth order term, our constant term, and then we can add a linear part to it. Right, so we've got some function. We add some part r minus re here, and then we need to add a slope to it. The slope is going to be the derivative of the potential with respect to position, evaluated at r equals re. Right, so that's the slope at that point. And then we have a quadratic term, r minus re squared times 1/2 times the second derivative of the potential with respect to position, evaluated r equals re. And then maybe we'll have as well a new term, which is proportional to the third derivative of the potential, which is proportional to r to the minus re to the third power. All right, well, let's think a little bit about each of these terms. So the idea with an anharmonic bond, we want to do something that isn't harmonic. And the idea is that at distances that are around r sub e, so close by, the potential is harmonic. So it looks like 1/2 kx squared. And then at r minus re greater than 0, far away from the bond, v of x will look like 1/2 kx squared plus more terms. All right, so the idea is that close by, like if I zoom into this region right here at the bottom of the potential that I've drawn here, right, it looks a lot like a quadratic function. Then as I go away, it starts to drift to another direction. Okay, so somehow the bond is getting weaker as a function of the distance. The spring is getting less stiff as it stretches. Maybe it gets more stiff as it stretches. We'll have to think about how that's going to, what physically this potential is going to deviate as the atoms get closer or further apart. We'll have to think about that. But whether or not this becomes more sharp or this becomes more shallow, as we get away from this box, it's going to be dependent on the value of cubic term, and then there's going to be a quartic term, and so on and so forth. All right, so let's think about this a little bit. So we've got this potential. Who is texting me right now? Oh, spam. Okay, great. So we've got this potential, and this is kind of the region close to the, like that looks, this is the quadratic looking part. Right, and so if we expand v sub x around R sub E, well, the first term we have is the potential evaluated at R sub E. Well, this is 0, right? We define this to be 0. It's the potential evaluated at the equilibrium point, which is 0. So that goes away. The next term is dependent on the slope of the potential at x sub is equal to R sub E. Sorry, I'm using R, not X. R equals R sub E. But the slope of the potential at this point is 0, right? Because it's a minimum. Right? So this is 0 because potential is minimum. Right? The first derivative of a minimum is 0. It's flat there. Okay, so that term goes away too, so we don't have to worry about it. All right, the first non-zero term is this is the second derivative term. And so the question, of course, is what is this second derivative value? Well, what if I wrote this as 1/2 k r minus re squared? Right, well, that's just the potential, the harmonic potential. So the second derivative of the potential, right, which is something to do with around the curvature of the potential, how curved it is at the bottom, at the minimum. Right, this is pointing up. So the second derivative is positive. It's a minimum. The second derivative is positive. Right, it's convex up. And k, and that just relates to k, right? So k is just the second derivative of the potential. Right, so this is k. Right, so we've already figured, right? So that's in some sense what k is telling you. K tells you, just like we saw, it's the stiffness. It tells you how much energy you have to put into the spring in order to stretch it a certain amount. Right, and as k gets bigger, this becomes more sharp and more curved, which means that the energy rises faster as you displace left or right. Right, it takes more energy. So as the curvature gets smaller, the bond gets floppier in some sense. Right, so the second derivative tells us something of potential is the force constant or the stiffness. Right, the stiffness tells you how sharp the potential is. Right, so that's the harmonic term, right? So what we've done is we started from the beginning. We just assumed a generic function that has the potential of 0 at its equilibrium point. It's a minimum at its equilibrium point. And because it's a minimum, the second derivative has to be positive. Some value positive, and that value is k, just by comparison. So if the system starts to deviate beyond this local region, right, starts to become anharmonic, those all appear in terms that are larger than x squared. Right, so in some sense, we have the harmonic part. Right, which is just the second derivative term. And then we go to the next term, 1/6 times the third derivative. And then there's a fourth derivative term you can imagine. Right, these are the terms that introduce the anharmonicity. These are the anharmonic terms. Right, and this is just a complicated way of saying that if we treat this system with a potential that is a polynomial, 1/2 kx squared, then any sort of anharmonicity that appears in the system due to the fact that the bond isn't perfectly harmonic appear in the third and the fourth order terms or something higher. And in fact, usually the third order term is about as much as you need. Right, we're going to see what the consequences of these are very soon. All right, so what I can always do is just write generally for any vibrational system, I could write the potential where x is equal to r minus re as 1/2 kx squared plus 1/6 times some gamma number, which is just a number that we can measure, times x cubed plus 1/24 gamma 4 x to the 4th, where gamma 3 and gamma 4 are numbers determined experimentally. Experimental numbers. Okay. All right, so the potential, just as we get further and further away from equilibrium, the potential is going to deviate by a small amount proportional to x cubed or x to the 4th. And in fact, these terms tend to scale, we can look at it in a little bit. These terms tend to scale by about a factor of 1,000. All right, so the idea is that at low energy, the vibration of a molecule looks harmonic. And then at 1 part in 10 to the 1,000, or 1 part in 1,000, gamma 3 is about 1,000th of the size of K. You start to see the anharmonicity appear, okay? Where the bond isn't quite, where it doesn't quite act harmonic, right? We're going to have to think about what that means, what it doesn't mean to be harmonic, right? Well, how does that show itself? So in terms of potential, what it does is it adds a little bit of curvature that isn't quadratic anymore. But what does that do in terms of the observables? Right, we're not really measuring the potential, right? We measure energy levels. So when we include this little extra term, due to this thing kind of bending in the opposite direction, the potential changing from harmonic to anharmonic, it's going to change our energy levels slightly, right? Our potential now is not x squared, but it's x squared plus a little bit of x cubed, maybe a little bit of x to the 4th. And that's going to change our energy levels a little bit. Right, so, yeah, go ahead.
So, I mean, I might be thinking too far for this, but when you're talking about like those being experimental numbers, right? So like, how could you find that? Because like, isn't an infinite number of?
I'll tell you in just a second. Hold on to that thought. So, Monica asked a great question. How the hell do I determine those? Let's go ahead and figure that out. Right? So, let's think a little bit about how we think our potential in some sense should deviate from x squared as we get smaller and as we get longer. Okay, so let's think about those deviations physically. All right, so let's start with a molecule AB, right, that we have set at the middle of its position, R sub B. Okay, so here R is R sub B, and we can say that the potential near the minimum of the potential looks like 1 kx squared. Right. Now what I want to think about is what should happen to my potential, the energy between the atoms, as I start to stretch it or as I start to push it together. All right, so let's consider what new forces appear or disappear as x changes. All right, well, as x goes, so as r goes to, let me call this r, sorry. So as r goes to 0, right, as we start to bring the atoms in closer and closer together, right, eventually I'm going to have it that they're almost butting up against each other. Right, so I've got these two atoms really close together. They've got a spring that has some restoring force that wants to bring them apart, but there's a new force being added here. There's a new force, which is the repulsion of the electrons. So the electronic exterior of the atoms. Right? Remember what an atom really looks like. If I were to zoom in a bit, right? If this is the atom A, inside of this atom, there's a tiny little nucleus of positive charge. And then there's a negative shell on the outside, right? A negative shell on the outside. Right, remember, electrons have no physical size. They have some effect and other electrons can feel them. But it's not like this area is like opaque and completely filled. There's a shell of diffuse electron density around it. It's negatively charged with this little positive, very massive part in the middle. Right, and you can think, well, if I bring in another atom, do it like this. Here's my atom B. It also has this positive charge inside of it, but it's also surrounded by a bunch of negative charges. Sorry, that's a minus charge. Right, and what do we know about two minus charges, right? They want to spread apart, right? They repel each other. So we have electrostatic repulsion. And it turns out that this goes as, so this repulsion goes as R to the minus 10. Right, so as they get closer and closer together, that force goes as R to the 10th, right? So it blows up really, really fast. All right, so what that means is that at close distances, the potential doesn't go as x squared, it goes as x to the 10th. Okay. Right, this is much, much stronger than the potential, the restoring force of the spring. Now these electrons are interacting with each other, they're repelling each other, and they repel at R to the 10th instead of the repulsive force of the spring, which is R to the 2. Right, so this dominates, right? This dominates at small r. Now, what about at the opposite distance? What about r goes to infinity when the atoms are really, really, really stretched apart? Now you've got these two atoms. Just kind of do it the same way I drew it before. R greater than R sub e. So now what we have are two balls of charges. From the exterior, these look largely like negative balls, but they're really, really far apart. They don't really repel each other anymore. And you've stretched this bond enough that the bond is starting to fall apart as well, right? What we've done is, in some sense, if it is a covalent bond, we're starting to break the covalence, right? We're not sharing that many electrons between them anymore. Right, so one thing here is that covalent bond is broken effectively, and what's left is just the dispersive interaction between the two particles, which is attractive. It's that van der Waals force, that weak force we feel between two atoms that are otherwise non-interacting. Right, so this is attractive force from van der Waals. Effect. And this goes as R to the minus 6. Okay, so what we have near the center of the bond, a potential that looks like R squared. That looks like a quadratic. On the short end, it balloons up as R to the 10th. Right, so it's got this really, really sharp close edge. And then on the exterior, we've got this thing that decays as R to the 6th, a little more slowly. Right, so on the edges, right, I should have probably convinced you that on the edges, it doesn't really look like a bond anymore, right? A harmonic bond looks like x squared. But on the short edge, it looks like r to the 10th, and on the long end, it looks like r to the 6th. Most importantly, another thing that we know is that as the atoms get even further apart, their potential should go to 0, right? At R infinity, E of infinity is 0. Right? If two atoms are infinitely far apart, they don't talk to each other. Okay? That should make sense. All right, so at long distances, the potential is 0. At short distances, the potential is extremely high energy. And then there's this Goldilocks region in between. Right? That scales as r to the 6th on the long end and r to the 10th on the short end. All right, so let me draw that function for you now. So a sketch of the function. All right, so we'll pretend plot V of R here. R. And we'll mark some part R sub E. Okay, and what we're going to define V of 0 means no interaction. So this doesn't mean that there's no restoring force. It just means that there's no interaction. No interaction. All right, so we know at a long distance that this goes to 0. Right, and as the atoms start to get closer together, they start to attract slowly as r to the 6th. So this should decrease. Right, and remember, in the center of the potential, it should look like a quadratic function. So in the center of the potential, draw this negative. In the center of the potential, we should have something that looks quadratic, like that. Right? And this thing goes as r to the 6th, so it kind of just smoothly rolls off in this direction, like this. So this is 1 over r to the 6th behavior. And then it blows up as r to the 10th. On the short end. All right, so we have this potential that's very, very steep on the short end. It goes to a negative bound potential down here that looks quadratic, and then it rolls off slowly to an asymptote at a distance.
I have a question.
Yeah, go ahead.
So how can you go now, like that part of the image box, it's negative now, does that not matter?
It doesn't. I've just scaled, right? I've changed V of R. I've changed my V of R, my definition of 0 to something else. So here I've set V of 0 potential means no interactions between the two atoms. And then infinite would be an infinite repulsion energy. So there has to be some positive, there has to be attractive energy between them as they come together. So it has to go negative.
So what about initially though, when you were talking about like, when I understood that you were saying, oh, the derivative is a minimum, so it's 0. But
Yeah.
now, like there.
Yeah, well, I would have to change, right, so the only thing that changes in this case with our Taylor series analysis is that you would set this to a negative number now.
I see.
It's just everything's vertically scaled negative.
Okay.
I've just scaled everything down. All right, and I'm just using that because I want to use my reference. So in the potential, when I had a harmonic potential, I said V at R sub E equals 0 because you can't escape the potential. There's no state lower than that. So I said equal to 0 here, but now I've got this new state, which is no bond at all. We know that a bond is more stable than no bond at all. So if I set this equal to 0, that means the bond has to be made there. I could shift everything up by that difference, and we will do that in just a minute. And I'll come back to that. It's just a matter of scale. All right, so we've got this potential that's got a couple different behaviors. Locally quadratic, it rolls off smoothly towards an asymptote at long distance and then balloons at short distance. Okay, there is a nice functional form of this potential. And it's what we use in spectroscopy all the time to talk about bonds and the vibrations of bonds. Right, so this version, a model version of this potential call this what's called, named after its inventor, the Morse oscillator. All right, and this has a potential. I'll write it over here. It's got a slightly different potential structure. I'll define everything for you. Let me change it to R. E to the minus alpha, R minus R sub E, all squared. All right, so let me go ahead and plot what this looks like. And I'll talk a little bit about why we choose this potential, why this is so convenient, and why it actually satisfies everything that we just talked about. Let me make this a little bigger. Oops. All right, so let's look a little bit about how this, I have some new terms here, D sub E and alpha. I'll answer what those are in just a second. All right, so let's think about how this function behaves at different values of R. Well, if R is 0, if R goes to 0, this is e to the minus small number. That's 1 minus an increasingly larger and larger number. We square it, so you get a positive number. So at small r, this balloons to infinity. So at small r, this balloons to infinity. What happens at long r? Well, this number becomes e to the minus large number, which is 0. E to the minus large number is effectively 1. E to the 0, which is 1. 1 minus 1 is 0. This goes to 0. No, it doesn't. Sorry, this goes, I start over again. At large r, this goes to 0. So we have dE minus times 1, so it's just d sub E. So this system at long distance has an asymptote at d sub E. Like that. And the function basically from here goes down, it becomes quadratic at r sub E, and then decays off quadratic or asymptotically towards this number d sub E, like this, d sub E. Right, and this is r sub E right here. Okay, so this has all the behavior that we want. It doesn't look quite like the function that we wrote down. Right, we talked about r to the 10th and r to the 6th, but this function gives us all the same behaviors. Okay, this has some really, really convenient properties that we're going to go through this week. All right, so in reality, this is what a bond potential kind of looks like. In fact, most bond potentials, when you measure them experimentally, what you can do, especially for diatomic molecules, you can actually do it spectroscopically. You can actually determine this potential through spectroscopy. They all kind of look like this. Okay, it's just a classic example of a diatomic potential. The idea is that locally it looks quadratic. You have this roll off, this slow roll off due to the van der Waals effect at long distance, and then you have electrostatic repulsion driving the energy up at close distances. All right, but let's think a little bit about how the potential behaves as we start to move away from the harmonic center of this. All right, so if I zoom into this region right here and say, hey, that looks a lot like 1/2 kx squared. Right, but as I start to include additional regions here, so I start to make the regions bigger and bigger and start to zoom out, right, you can see that this function no longer looks like a quadratic anymore, right? It has a curvature change. A quadratic function is monotonically increasing. It accelerates and accelerates and accelerates, but this is actually rolling off in the opposite direction. Right? So this has a different second derivative. This has an inflection point here. Right, so in order for a polynomial to have an inflection point, it needs to be at least x cubed. Right, so as I get to higher and higher regions of the potential, right, I can kind of approximate them with higher and higher order terms. Eventually, as that my system gets higher and higher in energy, what's 5 factorial? 24 times 5, whatever that number is. I have no, 120 gamma 5 x to the 5. Right, so as I start to get higher and higher energy, right, the idea is I'm adding new chunks to my potential as my potential gets bigger. So I'm zooming out. Right, so if I zoom in really close, it looks like 1/2 kx squared. As I start to zoom out, it looks like a cubic function. The cubic part starts to appear. I zoom in 4, I need to have an x to the 4th term. I zoom in even more, the x to the 5th term gets bigger, and so on and so forth. All right, so this basically smoothly kind of increases, and as I get to higher and higher and higher energy, I can approximate this polynomial of a higher and higher series of terms. All right, so this is a potential that's just basically getting more anharmonic as it gets bigger. Right, so this is the idea is that we're smoothly turning on anharmonicity. Okay, so the question, and this is what comes back to the crux of Monica's question is, what the hell does this do to our spectrum? What does this do to our vibrations? And the result is actually really, really simple. We'll actually go through it carefully next class. Let me just kind of introduce the idea to you. And we'll look at it more carefully next class. And I also have some pictures for you as well. So remember in the harmonic limit, right? So the key is to look at the spectroscopy. In the harmonic limit, remember that the energy values are h bar omega v plus 1/2, which means that the difference between the v and the v plus 1 levels is not dependent on v, it's just h bar omega, right? Equally spaced. So now what happens when I bring in my Morse oscillator? Well, the Morse oscillator, because it's put, and some say again, let me just go back one more time. Right, as I get higher and higher in energy and the potential, the system becomes more and more anharmonic, and it just kind of smoothly turns on. So when I'm at really low energy, it looks harmonic, and then as I get to higher energy, it becomes more anharmonic. And the energies do precisely the same thing. There's a harmonic term, v plus 1/2 times h bar omega, and then there's going to be a new term that appears that's smaller in magnitude, but causes a anharmonicity to it. So the way this works, and this is exactly how it turns out in experiment, is that there is a harmonic term, h bar omega v plus 1/2. It's the same as before, but it gets modified by a new term, h bar omega times this new number x sub e. X sub e is called the anharmonicity constant. And that's multiplied by v plus 1/2 squared. This is the first anharmonic term. And there's another term that's very small. We don't really have to worry about it in this class. That's usually the 1/3 to the cube power. I'll just kind of write it just as a say, right? So there's another term plus H bar, I forget what it's called. It's omega times Y squiggle E V plus 1/2 cube, right? And so this term comes from the cubic part, potential. That's the 1/6 gamma 3 x to the 3 part. And this part, the green, comes from the quartic part of the potential, 1/24 gamma to the 4th x to the 4th. And of course, the first part comes from the cubic part. All right, so what happens is now the energy levels are no longer equally spaced anymore. All right, you'll look at this a little bit on the homework, and you will do it certainly in lab next rotation. But if you look at delta E V to V plus 1 for the Morse oscillator, you find out that this is equal to omega E, H bar omega E times 2 bar H bar omega E XE V plus 1. So what happens is that your energy levels are no longer equally spaced, right? Harmonically, they're equally spaced, H bar omega E, but now they're starting to come together as a function of E. They're starting to close together proportional to this anharmonicity constant X of E. Every time V increases, this gap between them gets smaller and smaller and smaller. All right, so what we get now is that the energy levels are no longer equally spaced. No longer, but collapse as E or V increase. All right, so this is the big determination, is that if you see what you should see in an anharmonic oscillator is it takes so much energy to go from 0 to 1, takes H bar omega, and then you find it takes a little bit less energy to go to V equals 2 from V equals 1. And then you'll find it takes a little bit less energy from go to 2 to 3, and then 3 to 4. Right? And it goes as V plus 1. It's linear in V. Up to second order, which is this term. This term will include a V plus 1 squared term, and so on and so forth. All right, so what happens is that an anharmonic bond is no longer equally spaced. So you don't have equally spaced lines in your spectrum. We'll talk about that next class. But now you have lines that are no longer equally spaced. They're converging. It gets small, the gaps get smaller as you go. That's something you can determine spectroscopically. And we'll look at that carefully next class. Hopefully that answers your question. Yeah, so what we'll walk through, the homework actually walks you through this, and we'll talk a little bit about next class, is that these terms, this omega E XC, this omega E term, these are things that we can determine from spectroscopy. I'll show you a bunch of examples of that on Wednesday. All right, and what we can find is that if we know this value of XC and this value of omega E, we can determine all sorts of different properties of our molecule. Right, we'll work out some of the math, and in fact, one of the labs in rotation 3 goes through this math pretty in depth. One thing I wanted to look at is this d sub e number that I've included, this constant on the outside. All right, what does this number actually mean? Well, this number is how much energy it takes to go from the bond length, the equilibrium bond length, which is at V equals 0, to V equals to R equals infinity. Right, so this d sub e in some sense is the strength of the bond. Right, d sub e is the strength of the bond. The bond dissociation energy. That's a very useful number. We like to learn about bond strengths. And the question is can we learn anything about d sub e from the spectrum, say the energy levels? Well, one thing that we notice is that as the energy gets closer and closer and closer to this d sub e, as we get to the point where we start to stretch the bond, it starts to break, these terms become pretty big. The higher order terms become pretty large. Right? This becomes very non-quadratic. It's going to zero. Right? So the derivative is approaching zero or equal to infinity, which a quadratic potential never does. Well, these small terms are getting very big out here. And so the energy levels are getting really, really close together, right? So the spacings between the energy levels tell you in some sense how close you are to d sub e. The closer you are to d sub e, the smaller and smaller the spacings between the levels become. And what you can show, and this is actually quite cool, where am I going to put this? I'm just going to put it up here. It's a really dumb place to put it, but that this d sub e, which is the bond dissociation energy, is equal to omega e over 4 x sub e. So the dissociation energy tells you something about how fast the system becomes anharmonic, the size of this term, this anharmonic term, relative to the harmonic term. So if the anharmonic term is really, really, really small, meaning that this anharmonicity is very, very small, that means that you're approaching the dissociation limit very slowly. Right? Or the dissociation limit is what brings the anharmonicity on, it turns it on. So if omega e is much larger than x sub e, you have very large bond dissociation energy. This term is very, very small, and therefore your energy levels are very harmonic. But as the system becomes more anharmonic, or say the closer you get to the dissociation, we get higher and higher energy, x sub e gets larger and larger and larger. And so therefore the dissociation energy gets smaller and smaller and smaller because at fixed energy, you're getting closer and closer to that limit. And again, the idea is very simple. This gap in some sense between here and here determines how quadratic it is in the local region down here. And as this gap gets smaller and smaller, this becomes more quickly, more and more anharmonic, meaning that the second, the third, and the fourth and the fifth order terms become bigger faster. Therefore, x sub e is bigger, and therefore dissociates faster. All right, so by measuring the energy level spacings and how they vary from harmonicity, actually it tells us something about the bond strength of the molecule. Right, and then you'll actually use that in the iodine lab in the third rotation to determine the bond strength of iodine by measuring this anharmonicity of the iodine bond. All right, so let me just show you real quick, last minute, just what the Morse oscillator looks like as a comparison. I just have a little bit of code here, and then we can be done. So here's a Morse oscillator for HCLs. This is, again, what the wave functions look like for the harmonic oscillator. This is what it looks like for the Morse oscillator. First couple of levels. And the thing that you can really notice is because this thing is anharmonic, meaning that there's this dissociation limit on the outside, the bond is much more extended towards long distances. There's much higher probability for the bond to be over here than over here, because this is very, very sharp and this is much shallower. Right? So there's much less penalty to stretch long than there is to stretch short. And you can see that in the wave functions here, right? There's a significant, as V increases, so down here again, it looks kind of like our typical bond, typical wave function. But as V increases, you can see more and more amplitude outside the potential. Like this is a real good sign of anharmonicity. You have a bond that's anharmonic in the sense that it's biased towards longer distances, not only longer distances, but being outside of the turning points at longer distances than it is at shorter distances. You have the system that prefers, in some sense, to be longer than shorter. And so in the Morse potential, some of those averages that we take, that we expect to be zero because it's symmetric about the center of the potential, are not true anymore. At the average position of the bond in one of these states is no longer in the middle of the potential anymore because there's this extra probability density on the right side that isn't on the left side. So what it does is it shifts, the anharmonicity shifts the bonds longer on average. So a very anharmonic bond tends to be quite a bit longer than you would expect from a typical harmonic bond. All right, and one of the cases where this is really, really obvious is in, say, for instance, water. The OH bond, say, in a hydroxyl group, for instance, is extremely anharmonic. And that hydrogen loves to just be plucked off, it loves to tunnel, it does all of that. Loves to do that because there's so much probability density outside the potential long distance. So there's a lot of probability you'll find that hydrogen far away from the oxygen where it's easy to pluck off. It's all built into this idea here. And if we bring this dissociation energy even lower, the probability of finding it outside of the potential on the long end side becomes even greater. Okay. So we'll look at this a little more carefully in the next class. We'll do some spectroscopy on this problem. Think about vibrations. And that'll get us nicely set up for everybody test. All right, have a good one. Hi, what's up? Yeah. Yeah, let me send you the solutions right now.
Well,
I don't think any time